Okay, so let me know when you can see my screen.
Your slides, they look great.
Okay, wonderful. So now I just need to do the usual thing and hide this annoying panel. There we go. Okay, and get my pointer and we'll begin. Yeah, so good afternoon, everybody. Thank you so much for the invitation to speak at this workshop. Some really interesting presentations and stimulating discussion already. So I'm going to be talking today about climate prediction and projection, and I'm going to make first some sort of general arguments, I think, about justifying why we need better data, we need better models, and I would argue that we need better approaches to unifying the data and the models. And I'm going to speak then in the sort of second half of my short presentation here about one specific project where we're trying to do that, and it uses AI, it uses a machine learning model, and actually the visualization that you're looking at here on the screen is of that very complicated but beautiful when you visualize it neural network, right? It's a convolutional neural network that was developed by my graduate student at the time, Fraser King, and he also produced this quite stunning visualization of the network itself. I added this part here to show that it's related to the system that wasn't actually part of the original. Okay, so just to set the scene then and make this point that I'm going to argue for the sort of need for better unification and better approaches to bringing data and models together. This is the current state of the problem, right? This is global climate change, both in terms of the observational record of global mean surface temperature up to, as was, 2015 or so in the latest IPCC report. And then these colored lines going forward represent different scenarios, different answers to, what if questions about future climate change and how much warming could be realized if, emissions follow a particular pathway. And of course, we sit here in 2023, somewhere already into, this future projection region. And of course, there's big unknowns, right? We don't know exactly which of these lines we're going to follow. And I'll speak more about those sources of uncertainty that contribute to whether or not we're going to be up here or down here momentarily. But of course, this is a global average. This is a single number to represent the whole of Earth's climate system. And it's not particularly useful if you are in charge of making decisions about infrastructure or where to, relocate populations or anything, important to do with climate change adaptation. So we actually need to do a lot better than this, and we can do a bit better even at the moment, right? We can get these sort of spatially resolved maps of temperature here on the left or precipitation on the right. And so you can start to see some of the complexity, right, of the system, similar to what Francis was talking about earlier this morning, right? The spatial distribution of regions of the world that at 2 degrees global warming will become wetter, those of the world which we are fairly certain will become drier, and the different magnitudes of those responses. And so some of the complexity is here. But actually, even this is not really enough, right? The resolution of the models that are used to generate these images is still fairly coarse, maybe 100 kilometers on a side of a grid box. It's not really enough to make kind of quantitative local scale projections. And moreover, it's not just the spatial scale, but the temporal resolution of climate extremes that is very likely to have the biggest impact on individuals and the biggest consequences for things like infrastructure. And so, climate change, this is where the rubber meets the road, right? As to coin an old phrase. So in terms of extreme events and the impacts that climate change is having and will continue to have on individuals' lives, this is how it's going to be experienced. And it turns out, as a sort of nasty coincidence, I guess, that these extreme events, both in temporal and spatial extent, are the most difficult to model and the most difficult to observe. And so we're flying blind in a sense, right? Because we don't know what we don't know yet in terms of extreme events. And this is a big problem. So I already alluded to some of this, but the sort of sources of uncertainty that climate scientists tend to worry about can be broadly categorized into 4 groups. The first is related to which of those what-if scenarios we're going to follow, and this actually relates more to the governance and the mitigation decisions that are being made by international agreements and treaties and lots of other socioeconomic factors. So a lot of this stuff is well outside of the realm of anything that I'm qualified to speak about or comfortable with. And so as climate scientists, often we're just presented with these scenarios and asked to run these experiments in our model. So I just think of these different colored lines as being sort of different possible futures that we might follow, but they do contribute a very large degree of uncertainty to our projections. Then there's physics uncertainty, right? Our representation of the processes within our numerical models, and it's no coincidence that I've represented this with an image of clouds, because clouds and cloud processes still today represent the biggest source of single source of physical uncertainty in our numerical models. The next source of uncertainty is perhaps a bit less well discussed, but is equally important, and we've done some work in this area as well. The fact that we have those very large grid boxes, the relatively low resolution in our global models, means we have to represent some processes like convection and precipitation through what we call parameterization. These are sort of pseudo models that sit within the primitive equation models that Francis was mentioning earlier. And of course, if you have parameterizations, it means you have parameters, and if you have parameters, you have uncertainty related to those parameters. And you can see that depicted in this spaghetti plot here. And last but certainly not least, and actually this will relate to the example that I'm going to describe in a moment, observational uncertainty, because even our knowledge of the surface temperature of the Earth, something as fundamental as that, is still fairly incomplete, actually, right? There are regions of the world where it's virtually impossible to locate a thermometer, like the Arctic Ocean, for example. And so there are regions of the world where we're having to kind of fill in and interpolate between data. And satellites give us our best chance of doing that. But of course, satellites haven't been around as long as thermometers. So we have observational and instrumental uncertainty as well. And so I'm not going to have a huge amount of time to talk about it, but hopefully, given the subject of the other talks in this session, hopefully in the discussion this will come up. But my view, my vision, maybe my hope is that this amazing black box here, and it's no surprise that I've represented it this way, of AI, machine learning, could potentially act as an integrating technology, right? A way where we can combine some of the sort of most desirable and most important information from these different sources of data, and also quantify things like the uncertainties. It was already mentioned one of the earlier talks using Bayesian approaches, for example. So this black box is doing a lot of work in this slide, but my hope is we can have more of a conversation about how this might look. Okay, in the small amount of time that I have left, I'm going to jump forward and talk about one specific project where we're using AI to hopefully improve our extraction of information about the climate system from remote sensing data. Okay, I'm going to skip over this, but just to say there's been a very large increase in the amount of attention paid to machine learning and climate. Okay, this is a project that was led by Fraser King at the University of Waterloo in my research group, but with many co-authors who contributed to this project. And the paper came out fairly recently in Atmospheric Measurement Techniques. If you want to read more. Okay, so this is really the sort of summary slide of what we're doing here. So the idea, the concept here is that it would be very useful to be able to measure precipitation in both liquid and solid forms, such as rain and snow, using radar, right? Because if you can fly a radar on a satellite, then you can get global coverage, and you can really do a lot of good work in terms of peering inside clouds and finding out about cloud microphysics and structure. So as a sort of test for that, as a proof of concept, we're actually using a radar on the surface at these 9 different stations across the northern hemisphere that you can see represented by these dots. And so what this upward pointing surface radar is doing is basically beaming its radar pulses into clouds and then measuring the backscatter, the reflectivity that comes off of clouds and snowflakes and raindrops. And so that gives us a measure of reflectivity. And these clouds, I put this arrow here to sort of depict these clouds kind of moving across the station. And so it's beaming up these pulses and measuring the return echoes, the reflectivity every few seconds. And then we aggregate the data at a 20-minute scale. And at the same site, just next to the radar, we have this gauge, a traditional method of measuring precipitation accumulation with this pluvio2 gauge. And so the aim of this project is to create a regression model, a statistical model that can predict the accumulated precipitation as a function of the reflectivity that's measured by the radar. Traditional methods for doing this, traditional retrievals, are basically done by making lots of assumptions about the cloud properties and the physical distribution of the hydrometeors, and by imposing kind of strict relationships, power law relationships that are specific to one location, to one site. And so we wanted to create something that was sort of agnostic or could generalize between different sites. So it could potentially be deployed on something like a satellite mission in the future. This is all the data. I don't want to get into the details, but we do have a lot of data with which to train this regression model from all these different sites, and you can see the sort of density plots here of things like reflectivity from the radar, but it's a Doppler radar, so it also gives information about spectral width and Doppler velocity. And then we have some meteorological information as well from the site's temperature and wind velocity to go along with it. And here's the kind of flow diagram. And here's not a black box now, it's a green box, but this is the model that we're calling deep precip, and it's based on a convolutional neural network, and it predicts the accumulation of precipitation at the surface on these 20-minute timescales given these inputs. And to sort of cut a very long story short, what's shown in this bar plot on the right is that the traditional methods of converting radar reflectivity to precipitation all perform a lot worse than the machine learning models that I'm highlighting down here. And so on this measure of mean squared error, lower is better, right? So this is a very small mean squared error that's being shown here from the machine learning models. And so what we're arguing is that, not only is this a sort of better performing approach, but it actually generalizes much better as well. We haven't shown that here, but you can leave one site out of the training completely, and then the machine learning model can predict what the precipitation accumulation for a given radar reflectivity is at those sites that are left out. It's incredibly easy to generalize to new locations, which is very promising. And the other thing here is we're testing 2 machine learning methods. One is a random forest, and the other one is a much more complicated convolutional neural network that I showed that beautiful picture of at the beginning. And you can see that it doesn't look quite as impressive in terms of how much better it is, but the deep precip is consistently lower than the random forest, meaning it's doing a better job at representing the accumulation. I think I only probably have a few seconds left, but the other really nice thing about applying these machine learning tools to weather and climate data is that you can actually discover new physics by interpreting the model. Right, so people do think of these AI models as black box, and a lot of the time they are, but there are techniques like this Shapley feature analysis that you can do in a sort of posterior sense to inquire about and peer inside the black box. And actually, what we've learned through doing that is quite interesting information about the physics. And so, just to show briefly on these color plots here, the density, like the darkness of the shading, relates to how important a particular feature is of the input data. And so, this is vertical level with the surface or near surface down at the bottom and higher up in the atmosphere here. And so what we're finding is that you can get information, important information about surface precipitation accumulation, not just from the reflectivity that's being received by the instrument right above the surface, but also by peering much higher into the atmosphere, several kilometers in this case. And so this is new insight, right? Because it's not totally apparent just from physical principles why that would be. And so now we're digging into exactly where that relationship is coming from. So the AI can actually be useful at discovering physics as well as being good at predicting and retrieving. Okay, I'm going to leave it there, and I'm going to conclude. And I do look forward to listening to the other presentations and to the discussion that will come thereafter. So thanks very much, everybody, for the attention.